So the problem which we're going to look at involves a U tube which is filled with a number of different fluids. So we see we have oil here on the left hand side, below that we have air, and then we have water occupying the rest of the U tube. And what we've been asked to do is we've been asked to use the information which we have here, the different heights and the different fluid types, in order to find the ratio between the density of the oil and the density of the water. So to begin the question, we need to first of all understand what equations we can use in order to analyze the information which we've been presented with. So the first thing to realize is that this is a static system, so all the liquids are stagnant, nothing is moving. So therefore this falls in under the hydrostatic category. That means we can use the hydrostatic equations which we've previously developed in order to relate the pressures at different points within this system. We're going to assume that all of these fluids are incompressible, and therefore we know that the difference in pressure between any 2 points at different elevations in a static incompressible fluid is given by the pressure at point A at any point A, say up here, minus the pressure at point B is equal to the density minus the density of the fluid multiplied by the acceleration due to gravity multiplied by the elevation at point A minus the elevation at point B. So what we're now going to do is we're going to start applying this equation to this system, and we're going to see what information we can gather from this and whether that's going to allow us then to determine the difference in density between the oil and water. So let's first of all apply this equation to the right hand side of our U tube here. If we define a point 3 as sitting here at the very bottom of this vertical column of liquid, now we can apply this equation between points 2 here and point 3 here at the bottom. And the advantage of doing this is we know that the point 2 here is open to the atmosphere, which means that we know that this point is at atmospheric pressure, and therefore we only have one unknown pressure in our system, allowing us to solve for the pressure at point 3. So if we apply this equation between points 2 and points 3, we can say that the pressure at point 2 minus the pressure at point 3 is equal to minus the density of water multiplied by the acceleration due to gravity multiplied by the elevation at point 2 minus the elevation at point 3. So filling into this equation, we can say that we're going to use gauge pressure. So therefore atmospheric in this case is going to equal 0 Pascal gauge, as it's open to the atmosphere here at point 2. So therefore we have 0 minus pressure at point 3 minus the density of the water times the acceleration due to gravity multiplied by the difference in elevation between points 2 and 3 is equal to H4. So we simply fill this in, giving us an expression for the pressure at point 3, which is equal to the density of the water multiplied by the acceleration due to gravity multiplied by H4, the difference in elevation between points 2 and points 3. So now let's define a point 4 over here underneath the oil layer, and let's carry out the exact same procedure again. Now the reason we have to define point 4 as being at the bottom of the oil layer and not at the very bottom of the column is due to the fact that we have 3 different fluids in this left hand side column, and as you can see looking at our original equation here in the green box, we only take into consideration one density. So we're going to have to apply this procedure to each individual fluid in the left hand side column, and then we'll be able to join all the results together. So applying this approach between points 1 and points 4, we make the exact same assumption that the pressure at point 1 is atmospheric pressure, therefore it's equal to 0 Pascal gauge. And then acknowledging the fact that the difference in height between point 1 and point 4 is equal to H1, we get an expression for the pressure at point 4, which is equal to the density of the oil multiplied by the acceleration due to gravity multiplied by H1. So now again, let's follow again the exact same procedure. Let's define point 5 as being just at the very bottom of the air layer, and let's apply our equation between points 4 and points 5, this time using air as the fluid. This time, of course, instead of being able to say that the pressure at point 4 is equal to atmospheric pressure, we can actually substitute in our known expression for the pressure at point 4, which we obtained in the previous step and which is given here in the orange box. So substituting in this expression for the pressure at point 4, we're able to get an expression for the pressure at point 5, which is given here in the yellow box, which is the acceleration due to gravity multiplied by the density of the oil multiplied by H1 plus the density of the air multiplied by H2. So now at this point, we can define a point 6 here at the bottom of the left-hand side column of fluid. And now we can again apply the exact same procedure between points 5 and point 6. And again, what we have is we have an expression for the pressure at point 5 from our previous step, which is given down here in the bottom left-hand side yellow box. So we can substitute this in to our hydrostatic equation here. So doing this allows us to isolate an expression for the pressure at point 6, which is equal to the acceleration due to gravity multiplied by the density of the oil multiplied by H1 plus the density of the air multiplied by H2 plus the density of the water multiplied by H3. So now we have expressions for the pressures within the system at all these different points 1 to 6. But in order to solve the problem and to find the ratio between the density of the oil and the density of the water, we need to realize that the pressure at point 3 and the pressure at point 6 are equal to one another. And the reason for this is that they lie on the same horizontal plane. There is no difference in elevation between these 2 points. And if we look at our original hydrostatic equation in the green box, we can see that if the elevation is the exact same between 2 points in a static system, then their pressures must also be equal. So therefore, allowing pressure at point 3 to equal the pressure at point 6, we now get an equation which relates the different densities of the fluids to one another. So the first thing which we can do here is we can divide across by the acceleration due to gravity. So that essentially crosses that off from both sides of this equation. And the next thing we're going to do is we're going to make an assumption. We're going to make a simplifying assumption that if we look at the right hand side equation here, that the density of the air is significantly less than the density of water and the density of oil. So typically the density of air is about 1 kilogram per meter cubed, whereas the density of water is about 1,000 kilograms per meter cubed. So in order to simplify this expression for ourselves a little bit simpler, we're going to cross off the density of the air and we're going to assume that this is approximately equal to 0. And now we're left with an equation which simply relates the density of the water to the density of the oil. So rearranging this equation to get the ratio of the density of oil to the density of water, we see that this ratio is equal to H4 minus H3 all over H1. And filling in the values for these numbers, which we are given in the above diagram here, this boils down to 90 centimeters minus 30 centimeters, all divided by 70 centimeters, giving us the ratio between the density of the oil and the density of the water being equal to 0.8. So in this case, we found the answer to our problem by simply using this hydrostatic equation, which is up here at the top right hand side of the screen in the green box, which relates the pressure at different positions within any static incompressible fluid, which are at different elevations. And what we did is we remembered the fact that this equation relates to a single density fluid. Therefore, we applied this equation between different points within the same fluid, but then we were able to successfully add these results together in order to generate the result which we needed. So this was simply an example of how one might implement this hydrostatic equation and how you can use it in order to find out valuable information such as the pressure at different points within a static system, or as we did in this case, the relationship between densities of different fluids within a static system.